Reaction rate can be expressed in different ways. One way is average reaction rate, which is the change in the concentration of a reactant or product with time. Note that rate is a positive value. Take, for example, a chemical reaction in which reactant A is converted into product B. Rate equals negative delta concentration of A over delta time. The symbol that looks like a triangle is capital or uppercase delta. It is a letter of the Greek alphabet. It means change. Square brackets enclosing A are used to represent the molarity or concentration of A. Thus, in this equation, rate is the change in concentration of A over change in time. Change in concentration of A means final concentration of A minus initial concentration of A. Change in time means final time minus initial time of a particular period of time. Final time is larger and initial time is smaller. Final time minus initial time is therefore a positive number in the denominator. The concentration of A becomes lower after some time, since some of A is converted into B. The numerator is negative since a larger initial concentration of A is subtracted from a smaller final concentration of A. If the numerator is negative and the denominator is positive, the fraction delta concentration of A over delta T is negative. However, rate is necessarily a positive value. To ensure that rate is positive, a negative sign is added before the fraction delta concentration of A over delta T, since a negative fraction multiplied by negative gives a positive number. Rate can also be expressed in terms of the change in concentration of B over change in time. The equation involving the product B does not have a negative sign before delta concentration of B over delta T. This is because the concentration of product B increases over time and delta concentration of B is positive. The fraction delta concentration of B over delta T is already positive. The diagram at the top shows black reactant particles A turning into red product particles B over time. The graphs at the bottom right are plots of number of molecules against time. The black graph is that of reactant A, while the red graph is that of product B. At the start, the rate of reaction of reactant A becoming product B is fast, as the concentration of reactant A is high. If a high concentration of A is present, the likelihood of A particles undergoing effective collisions is greater. This is denoted by the black graph having a steeper slope or gradient at time zero. The steeper the slope or gradient, the closer the graph resembles a vertical or upright line. Numerically, the rate has a larger magnitude. The slope of this graph is also negative at every point since reactant A is being used up. Over time, there will be more B formed and less A present. If the concentration of reactant A is lower, the chances of A particles effectively colliding are smaller, so the reaction rate is slower. This is denoted by the black graph having an increasingly gentle or less steep slope or gradient beyond time zero. The gentler the slope, the closer the graph resembles a horizontal line. Numerically, the rate has a smaller magnitude. It is similar for product B. At the start, there is no product B, but once reaction begins, the conversion of A to B is quite fast since there is a high concentration of A to undergo effective collisions to become B. The rate of formation of B is greatest at the start, and this is denoted by the red graph having a steep slope or gradient. Over time, since some A has already been converted into B, less A is present to be changed into B. Thus, the rate of formation of B is slower. This is denoted by the red graph having an increasingly gentle or less steep slope or gradient beyond time zero. Both graphs have a similar shape. We can transform one graph into the other by flipping it over. Both rate equations are equal. Another way to express reaction rate is to find instantaneous rate. Instantaneous rate is the rate of a specific instance in time, that is a single point in time. The instantaneous rate of a reaction can be found at any point in time by finding the slope of the tangent. From the graph generated from the reaction between molecular bromine and methanoic acid or formic acid in aqueous medium, the tangents at 3 points in time are drawn and their instantaneous rates calculated. It can be seen that these rates decrease as time increases. Thus, the less steep the gradient or slope of the graph, the slower the rate. For the same reaction involving molecular bromine and methanoic acid, instead of determining instantaneous rate, average rate may be determined. Average rate of reactant bromine is final concentration of bromine minus initial concentration of bromine divided by final time minus initial time. Since bromine is a reactant, its concentration decreases as time passes. Hence, the change in concentration of bromine is negative. Change in time is positive. A minus sign is included before the fraction to ensure that average rate is positive. Different time intervals can be chosen. As can be seen from the calculated examples, the average rate for the first 50 seconds of reaction is different from the average rate for the first 100 seconds. Hence, average rate depends on the time interval we pick. Different time intervals give different average rates. Another thing to note is that the average rates calculated are different from the instantaneous rates, which are obtained by finding gradients of tangents drawn at specific time points. In the table, the last column shows instantaneous rates, which are different from the average rates calculated. Instantaneous rate is usually more useful than average rate. The table shows that the instantaneous rate decreases with time as concentration of bromine decreases with time. In what manner does the concentration of bromine decrease, and in what manner does the rate decrease? When we divide the concentration of bromine at the 50th second by the concentration of bromine at the 250th second, that is 0.0101 molar, divided by 0.00500 molar, we get roughly 2. When we divide the instantaneous rate at the 50th second by the instantaneous rate at the 250th second, that is 3.52 times 10 to the power of negative 5 molar per second, divided by 1.75 times 10 to the power of negative 5 molar per second, we get roughly 2 as well. By inspection, we notice that 0.00500 molar has reduced to around half of 0.0101 molar, and that 1.75 times 10 to the power of negative 5 molar per second has also reduced to around half of 3.52 times 10 to the power of negative 5 molar per second. The concentration of bromine is multiplied by a factor of half. The rate is also multiplied by the same factor of half. This means that the rate is proportional to the concentration of bromine. Rate can be written as rate equals K times concentration of bromine, where K is the rate constant. To find K, rearrange the rate equation to make K the subject of the equation. Then substitute a set of rate and concentration of bromine values at a particular time into this rearranged equation. The calculated value of K given here is obtained using the values for time equals to 50 seconds. How do we get K's units? K is equal to rate over concentration of bromine. The units for rate is molar per second. This is because the numerator for rate, being change in concentration of bromine, has the units molar, while the denominator for rate, being change in time, has the units second. The units for concentration of bromine is molar. Simplifying the units of the numerator and denominator by cancelling the identical molar, we are left with per second. By substituting other values of instantaneous rate and concentration of bromine at different times, it is found that the values of K obtained are all close to 3.49 times 10 to the power of negative 3 per second. That is approximately equal, as shown in the table. The slight differences may be due to experimental errors or even the way in which tangents at particular points are drawn. Thus, K is called the rate constant. The word constant means a number that is unchanging, that is, it stays the same. For the reaction of bromine and formic acid, the rate of reaction depends on the concentration of bromine. By plotting the rate of reaction versus concentration of bromine, a straight line is obtained. The slope or gradient of the line is the rate constant K. The straight line graph of rate against concentration of bromine is like a graph of y is equal to mx, where y, the vertical axis, is rate, and x, the horizontal axis, is concentration of bromine, and m, the gradient or slope, is the change in rate over change in concentration of bromine. K is the rate constant. It is constant at a given temperature. It does not change as the reaction proceeds.